Welcome to those of you who are traveling. Like as they said, I'm Dr. Schafer. This is my third year here at Texas A&M. This is a seminar talk, so I may kind of skip some parts and for the level of the group here today, but this talk is roughly just highlighting 3 papers that were published last year from my postdoc. So they are all motivated on time series data, and we are using this shrinkage prior. So I'll start with some motivation, kind of telling a story of how did I land in doing these types of models. Then I'll introduce this dynamic shrinkage prior. So this is a prior that we've been using and adapting in all of these papers to handle time series that have jumps, so change points, varying trends throughout time, like the middle one. Most of the time we have sort of a smooth trend, and then occasionally there are large jumps. That's what we say called non-stationary. And so estimating that smooth trend, that's the trend filtering part of these models. And some of our data are counts, so they are discrete integers. And then we have 2 approaches for estimating where these jumps occur, change point analysis. One is a fully Bayesian model, and the other is a 2-stage decoupled approach. Okay. So when I was a postdoc, I was part of this group, Predictive Risk Investigation System for Multi-Layer Dynamic Interconnection Analysis, long word. And our goal was, we had a large team. We had co-PIs from 7 or 8 scientific domains, all represented here in this graph. The big picture was, if we could have a measurement of risk in each of these domains, how can we associate them in time? What sorts of leads and lags lead to risk in another domain? So for example, we centered all of our analysis on the electric energy domain. So things like how robust is our energy grid? Is a risk in climate leading to a risk in the energy grid, et cetera. So that was a very big task that we were working on, and throughout our sort of assimilation of all the data, we were getting lots of data that were counts, non-stationary, and very noisy. So to associate all of those domains, we really wanted some smoother trend. So that's why we sort of went towards these Bayesian trend filtering models. And we started to describe these time series using this language here. So we describe this micro scale evolution, so where most of the trend is smooth, but it might be fluctuating, like seasonal trend as the drift of a non-stationary time series. And then sort of the macro level changes, and this screen you can't really see, but this is some jump in weekly power outages. That's sort of a macro level change you can see in the data, and we call that a shift. This type of behavior in data can be challenging for what I call a strict modeling framework. So maybe like a time series with 1 lag is sort of a strict hypothesis of how that is evolving. Okay. So all of our methods are model-based, they're all data-driven. So we have these adaptive model-based solutions. As I mentioned, we have 3 that I'm going to talk about today, where we're going to model this smooth trend as an extension of something called dynamic linear models. We have flexibility in our model form. We are not really specifying how many shifts there should be or how many lags. The dependencies. We're using something called global local shrinkage, so we can distinguish between these time periods where we have gradual, constant seasonal trends from these major shifts. Okay, we can detect change points in the presence of noisy data heterogeneity, and everything is in a Bayesian modeling framework, so we can have uncertainty around all derived quantities. And one of the motivations, right, was that those associations in the end, we could propagate all of our uncertainty from maybe this modeling stage into a second modeling stage. That's sort of motivation. Are there any questions? No, Bayesian. When I was a prospective PhD student, I didn't know much about Bayesian methods, so I'll try to explain in a way that makes sense. Okay, so this is a basic Bayesian dynamic linear model. So we're just thinking of one time series, so like the power outage I showed before as our YT. So we have at each time point one measurement. That measurement is conditionally independent on other measurements, so otherwise, but it depends on a mean theta t and then some noise, measurement noise. XT can be a covariate, although in all of our analysis, we just think of modeling the measurements as coming from a time varying mean. So just theta t. So X kind of drops out and we have one everywhere. So this mean theta t, this is what's going to drive the dependence in the measurement. So we put a model on theta t, the parameters that has some dependence. And the way we do that is with this integer, with differencing of our unknown mean theta. So if we don't difference, so if we have integer 0, then we're just saying the mean follows this normal distribution. It's just sort of a random mean everywhere in time. When we take the first differences, right, so we're taking the difference between consecutive means. This is, I'll show on the next slide, this is a random walk mean model. So your mean is centered on the last mean, but it has Gaussian noise. And then we often model things on second differences because this sort of differencing is related to how smooth. It's more of a user choice. We haven't really explored this as another parameter, but for most smooth trends, you can get a very smooth trend with second differencing, and then you only need to initialize the first two thetas, theta 1 and 2. When we get to change points, these have interpretable meanings. First differencing means we are sort of just looking for jumps in the mean. Second differencing means we can have piecewise linear trends as well. All right. So as I was mentioning, the other way to think about this is as a state space model where, again, our measurements Y are conditionally independent given some latent process or unobserved component, so theta. So we're thinking of theta here as our state space. And again, with d equals 1, we can rewrite that integer differencing as this evolution of our mean. So we have our mean is centered on the last mean with white noise. In econometrics, there's another popular state space model for the increments. So I'm going to be talking mostly about these increments omega, where we adjust essentially the variance of our increments, and the variance is time dependent. So this leads to stochastic volatility. So generally in a time series, you'll see this as your variance is growing over time. So these are two models that are related to what we did. And here's just a brief highlight of how these models behave when we have a lot of heterogeneity in our data or a large amount of noise. So this is all the same data, just 4 different model fits, all Bayesian. The first one is that random walk. So you can see it's very wiggly, very spiky, sort of chasing that noise, even though the evolution is in the latent process, it's still very much following the data. As we go across, this upper right and bottom left are both using Gaussian stochastic volatility for the increments, but Poisson likelihood and negative binomial likelihood, those are 2 distributions we considered for modeling the counts. Okay, so, and then the last one, this is our method, negative binomial Bayesian trend filtering. So we actually, our prior allows, you could see, hopefully, we get much smoother trends than these other three methods. And that's sort of our goal in this. So this is all a methods work. Yeah, Isaac.
Sorry, could you go back to the general Gaussian stochastic volatility model?
Yeah,
Where are the Poisson or negative binomial?
yeah, so that would be up here. Instead of having y as normal, we have y as negative binomial with a log mean theta.
I see, okay.
Yeah, and that, yeah, it's a little out of order. It'll be on the next slide. Yeah, good question. So yeah, those are for the y's. Okay. What was I saying? Oh yeah, I was saying that all of these methods we weren't trying to answer a specific scientific question, so we're just sort of developing this flexible. Okay, so before yeah, let's see.
So that you want the smooth pad, right? Like your method. Can you tell me the idea behind that? You want that?
Well, we just want to have a method that's robust to not chasing the noise of the data.
I see. Because the blue and yellow one is kind of like hitting every single point.
Yeah, and so those are the estimated mean process, so we would anticipate that the mean process is less dynamic than the data. So maybe you like this, as I was saying, it's sort of subjective. We're just sort of illustrating a method. But yeah, we're motivated to get smooth trends for associations later on. Although we didn't get to that. Okay, so before I introduce the dynamic shrinkage prior, this is sort of a little background on other works that are looking at estimating these smooth trends in time series. There's a series of work that applies global shrinkage, meaning, so again, we're talking about those increments, those omegas. We want to know when are they zero or not. And if they're non-zero, that's what allows our mean trend to fluctuate. Okay, so you can have global shrinkage, meaning you apply sort of everywhere equally. This is how much should be shrunk to zero. Then there's in Bayesian literature, there's sort of two paradigms for modeling shrinkage and selection. One is having so-called two-group priors, where you have an indicator that says whether or not your increment should be shrunk, and those that has a probability, and when it's turned on, shrunk, it'll have a very narrow prior around zero, and when the indicator is turned off, not shrunk, you'll have a very wide prior, so your increment can be anything. We are working off of this work, Cowell et al. In JRSSB in 2019, doing local shrinkage, which is the scale mixture prior, meaning that we don't have that latent indicator. Instead, we have a hierarchy where we're sort of mixing in the variance of the increments, and I will go into all of this now. Okay, so if you remember the Gaussian stochastic volatility that I showed, that was also similar to these first two lines where we have the increments, have a Gaussian distribution with some variance, and the log of that variance follows this autoregressive process. So that's very similar to the Gaussian stochastic volatility, but instead of having the sort of one global variance, we have two. You'll see tau squared lambda t squared. So we have the global part is the tau squared, and the local part is the lambda t squared. So tau is sort of like what proportion over the whole time series of my increments should be shrunk to zero or not. So it sort of says globally, how much sparsity does this process have? And then the lambda t, the local part, lets the model say, okay, globally I have this much shrinkage, but at this time point, I am not shrunk. That's the local. This specification, the rest of the priors, we have the innovations of the log variance, follows this weird 4-parameter distribution. Not going to go into a lot of details, but it's an inverted beta random variable. Okay, but you can ignore that. And with this specific specification, this prior induces horseshoe like behavior for shrinkage. So the people visiting, have we heard of horseshoe before? No, okay. Yeah, it's very much a Bayesian thing. You can think of it. Well, I'll show you on the next slide. Okay, but the horseshoe is a pretty standard prior these days for Bayesian variable selection and shrinkage. And here, what we're doing is adding autocorrelation to the horseshoe process, meaning that if I know at this time point that my increment is 0, it's very likely that the next increment will also be 0 in the way that we specified this model. And so in pictures, this is sort of what it looks like. So I have my increments, omega, and then I can quantify. So this is maybe a derived quantity, like I was mentioning earlier, this shrinkage coefficient. This is just a way to summarize what's happening at a time point. And if the shrinkage coefficient is 1, then it's 100% shrunk. So omega, our increment will be 0. So the shape of the prior looks like a horseshoe on the right. That's where the name horseshoe comes from. On the top left panel, that's the standard horseshoe that was introduced, I don't even know. Let's say, a while ago, 10 years ago, maybe. Horseshoe. Oh, I don't know.
I don't know, but it's definitely, I think it's more than 10 years.
Yeah.
Yeah.
Okay. I don't remember when it was introduced, but that's the standard horseshoe. So essentially, how you interpret that is your prior is saying you should either have it completely shrunk or not shrunk, right? If it was uniform, you could get weird properties in your shrinkage. As we go from the panels from left, sort of snaking down, that's where increasing that bottom correlation. So the distribution mass, it's pushed farther to the extremes 0 and 1. So we have a higher prior. So for example, this bottom one is, I think, autocorrelation 0.75 or something. So it's makes it very likely that you have a long run of zeros in your increments. Yeah.
When you say increment, are you talking about like, if we go to the weather example, like, not the weather, but the power outages, like how many more you expect the next month compared to the, okay.
Yeah.
It's like a slope sort of.
Yes.
Piece of linear, okay.
So yeah, if we do the second differencing, then the increments are, like slopes. Yeah.
Can I ask you a question? Can you please go back to the previous slide? Sorry, it's a question. I just don't know the model. So, but like, why do we need to demean? So, what is mu? Mu is like.
Mu is the global variance on the log scale.
Oh, okay, I see.
And
Sorry,
that
I first thought it was like the mean of the HD process.
It is the mean, but the
Oh, okay.
mean has the interpretation. It's just a one-to-one right here. It's just the transformation. So
Right.
interpreting it,
I see.
it's the global.
Yeah, so my question was like, why do we need to demean one to define HT? So when we in like the autoregressive part, why don't we have just like
Because
HT
it's
minus
not
1 or something? If you like.
zero. Yeah.
Yeah, so that was the question.
Yeah. Yeah, I think because we want it. I don't know, I never thought
Okay,
about that.
that's good.
I think we want that process evolution to be mean zero.
I see. So HT general is not stationary.
Yeah.
I see. Okay. I think it makes-
All right, yeah, good question. Okay, this is just another picture to show a little bit more about horseshoes. So again, in Bayesian literature, as I mentioned, like, you want to think about like normal Gaussian tails. If I put a Gaussian distribution on a parameter, like I can go pretty far from the mean, where if we look at these tails, just focus on the solid black line is the horseshoe. We have lighter tails than Gaussian distribution, so we again are more. So this is on the increment process. Before I was showing the horseshoe shape comes from the shrinkage coefficient, that kappa. But when you look at what does the prior look like for my variable, my increment, I have very light tails, so I will be very, very close to zero in general. Okay. I'm gonna probably skip this, but this is just saying that sampling is pretty, we can do Gibbs sampling for this process, this dynamic shrinkage, right? Okay, so this is an example of fitting that model. And I also have here on all the slides, code snippets, how you can fit these models easily. Currently, everything is in separate packages. I'm working to consolidate them all into one overarching package. But so again, we have a mean process for our data. This is simulated data with a change in mean. One, it jumps. So essentially, we have 3 regimes. We start in one regime, we jump up, and then we jump back. Okay. The red is the point-wise mean of the trend. So those thetas, and then the background, those are several samples from the posterior. So this is sort of the behavior we get, and then for the counts, we can just essentially change the y. Instead of being y is a normal linear regression, we will do negative binomial. This is motivating why we want to choose an integer valued process for our data, or sorry, distribution for our data. There isn't really a standard integer value time series. Like when we think of regular time series, we think of AR, ARIMA. That family of models doesn't really exist for counts. But we have count data in many applications, especially when we think about like aggregating point processes, like how many events do I have in this time frame, like without outages, we doing how many outages in a week. If you want really fine scale aggregation, you will get more and more zeros, which means we shouldn't take the log transformation. The more zeros we have, or the smaller our counts have, because we will not be approximating that normal distribution well. Also, any quantity you want to predict or summarize for your data, if you don't have a discrete distribution, you will not get discrete quantities and you will have inherent misspecification. And I'm also a believer that if you've seen log, y plus c, that little constant, this to me is not actually a tuning free transformation. Okay, I am happy to talk to you offline about that, more of a soapbox thing than anything. So yes, so this is the specification of the negative binomial, Isaac, that we use. So we use this specification where the log conditional mean is theta. And then we have the overdispersion parameter R. As R goes to infinity, this is a Poisson distribution. So we have done things like not sample overdispersion, set it to a numerically large value, and use this to model Poisson data. The reason, if you are a Bayesian in here, the reason we do negative binomial is the sampling. It's a little bit easier because we are doing this data augmentation scheme everywhere to do Fourier gamma rather than accept reject steps. We have conditional sampling. So the only difference here is now our data come from a discrete distribution, and this is the paper for this model. This is code snippet, again, pretty straightforward. And then this is a graphical representation of the model for one observation time, just sort of highlighting again that with this sort of state space model specification, there is no dependence at the observation level. The Y's do not depend on each other in any way. All of the dependence is happening at a different part of the model. And here it's specifically in this increment process. I always like to depict my Bayesian models in this way with a graph. Sort of highlights what's going on. Okay. So for some examples, this is just simulating. This is the true trend in black dash. I don't have the data plotted here, but the trend is in black dash. The blue is the estimate from that model. The first one, not really a model, it's just exponential smoothing. It's just a weighted average through time with decaying weights. And this is a pretty standard routine in econometrics, again, which is where my postdoc advisor was trained. So we have some crossovers with econometrics methods. This middle one is a Poisson fused lasso. If you're familiar with lasso, they have a penalty for increments as well. It's called the fused lasso. So they essentially do the same thing that we're proposing, where you shrink increments between consecutive coefficients. But this is an optimization method, so we don't have any easy uncertainty that we can quantify about this trend. And then as we go on, we have, if I assume my counts are Gaussian, no transformation. If I do a log transformation, and then finally our method. And so for the two Gaussian and log Gaussian, you see these black bars. That's highlighting all of the time points where the pointwise critical interval for the mean went below 0. Right, so we can't have a mean in this model that goes below 0. So those are essentially time points where your model has misspecified inference.
Great questions.
Yeah.
So usually for fields are so you get these step functions, right? So this looks very
Yeah, you can't really see, there are around the peaks, like sharp,
the black line is
the truth. Yeah, the blue is the,
estimate.
yeah, so
Okay, so
you
the-
can't really see, but
There's a lot of steps.
there are sharp, yeah,
There are like a lot of steps.
yeah. And I believe this is also on second differencing, so
I see.
you get piecewise linear,
Okay, I see.
yeah. Yeah, okay, let's see, I'll probably skip some of this stuff. Just sort of says we recover the mean well, and we are the only Bayesian method that reaches the nominal coverage. Meaning if I say I want a 95% critical interval, I cover 95% of the time. Okay. So this is the energy data that I showed before on the left. This was just highlighting 3 different types of behavior. So on the left, we have in Boston, had a generally much higher level of counts overall, and sort of one spike. Then Cambridge is just smooth across all the time points and very low counts. Plymouth has very low counts, lots of zeros around right after the 2016 mark, but 2 spikes. And yeah, I think the screen isn't showing very well. There are 2 confidence interval for the mean and prediction interval for the data. Okay, This is that shrinkage coefficient, just showing that. What that looks like. Just gonna skip that, okay. So any questions? Okay, so that was sort of background on estimating that smooth trend. Now we're going to talk about, okay, what if I want to have also discrete inference on when is there a change point? Okay. So we introduced this model, ABCO. We added 2 components to that model I already introduced. So the first one is on the data level. So here for Y's, we added an additive outlier process, zeta. You don't really need to pay attention to anything, but zeta is just a another latent process for additive outliers at the measurement level. We model it using a horseshoe plus prior, which is just like the horseshoe, but even sharper. So you have more zeros than a horseshoe. And then we can calculate this derived quantity based on our posterior, where at each time point, we can sort of label how much of the measurement variance is attributed to the outlier process at that time. If it's a large proportion, then it's likely that that is an outlier. The difference to the dynamic shrinkage is we don't have dependence for the outliers, so we're sort of assuming that these are non-correlated, just sort of randomly occurring outliers. Then for the change points, we are adding, and I will I can get into all the caveats, okay, but we add one thing here on the dynamic shrinkage, which is this. So we have a second autocorrelation and this latent indicator S. So we're using to model the change point process using this threshold autoregressive model. This allows us to not have to pre-specify like how many regimes we have. It does have some downsides, which I probably won't have time, but just so you know, this model is not perfect. Okay, so S is a latent indicator, so the binary 0 or 1, and there is a theorem in the paper that essentially says if I have a change point, then remember that horseshoe posterior was symmetric. This actually will make it asymmetric, and you'll have more mass to have a jump around a change point. Okay, yeah. Let's say so we only have 5 minutes, so let me. And then the autocorrelation prior is in the negative fields. So for when you think about dependence, if you have negative dependence, you can have those big jumps away. Okay. We summarize sort of, and then once you fit the model, you still have to decide from the model fit, when do you have a change point? So you can summarize how much of my samples for my MCMC told me that this time period should be a change point or not. What this proportion is. This is very much still like work in progress, but this is an illustration of if you do have very nice big jumps in your data, all of the components that this model can handle. So we have change points. Now we have Gaussian, we have stochastic volatility here as well. So you can see for some periods, the variance is high and then it goes low and then high. So that's what stochastic volatility looks like. Here, the blue markers are just marking when my proportion were high, greater than 50%. So I identified 4 change points. And then my anomaly score, again, this is what proportion of the variance for my measurements is attributed to the outlier process. So we only really have one here, this red one. Right, so you can see that this is a good feature of the model, right? All of these time points, these are not outliers, it's just that there's more variance at that time. And so we're able to handle all of that. Okay, I'm gonna skip some of this, because I want to talk about this one, maybe they have 2 minutes. Okay, and then this model was published in Journal of Business and Econ Stack. Okay. The last one I will just highlight is rather than making our dynamic shrinkage process more complicated by introducing this thresholding mechanism, there is this sort of two-stage approach we can take. So we adapted this from a paper from 2015 that was using this two-stage approach for Bayesian variable selection and regression, which is very similar to our motivation, right? Except we're selecting increments. Instead of selecting which features are most important, we're selecting which increments are not zero. Okay, so the first step is you fit any one of those models I already showed, and you get some MCMC samples in your hands. Okay, and then the second is you do a penalized loss to transform the posterior into a discrete inference. So we can separate the two components, the smooth trend from the discrete inference. Compared to other change point algorithms, we can have more insights by using our posteriors as some uncertainty quantification. So I'll just sort of highlight, I'll sort of maybe skip this, but essentially, once you have your MCMC samples in hand, you do this penalized regression, weighted penalized regression, and we just plug in for different components the posterior means that we have. So for the prediction, we plug in the posterior mean of the prediction, and then for our weights, we plug in the posterior mean of the variance. And then we use this adaptive L1 penalty, and the L1 penalty is weighted by the posterior mean of increments. So we have 3 quantities from our posterior, then we use this penalization to essentially find discrete inference. I'm going to skip a lot of this, but essentially this is what it looks like. So when you do your lasso optimization, you have your tuning, your this lambda, right? How much shrinkage it's there. You can go for different values of lambda will correspond to different number of change points in your summaries. And so this is just projecting the posterior mean and some posterior samples to the space identified by the optimization that only has one change point. So you just sort of repeat this for increasing model sizes, meaning how many regimes are there. So we could have essentially everything is 0. This is a projection of the posterior mean to 0 change points, 1 change point in blue, and 2 change points in purple. And again, these changes are determined by the optimization. Just like if you do lasso regression and you choose one lambda, it tells you which features to keep. Same thing. Yeah.
How do you choose lambda? Just cross validation?
Yeah, so that's here. So to choose lambda, so lambda corresponds to how many regimes you have, or how many change points you have, 0, 1, 2, etc. This is the workflow proposed by that original paper, Hanna Carvalho, and essentially use this goodness of fit metric, where this is like the dense trend versus the projected trend to a smaller space, right? So you can calculate this across your entire, so we get these box plots because we have our MCMC samples. So we project every sample to that lower space. we calculate this and then we get a box plot, and then you can sort of use this to choose the most parsimonious model that exceeds some goodness of it. So for this simulated example, it jumps up at 2 and then it flattens off. So 2 change points would be the most parsimonious model supported here. And so we apply this to these global temperature anomalies using second differences. So we can pick up on when does the rate change. We go through the same procedure here. Just notice the y-axis for no change points. We already kind of have a moderate goodness of fit. Okay, but then it jumps up at 1, and that 1 change point is here in the 1970s. So we detect a change in the rate of these global temperature anomalies after 1970. This is supported by the scientific literature. So we were pretty happy with that because we were not, as I mentioned, we didn't build this model to answer any of the specific questions, but we want to see, we wanted to still check if it matches what scientists already are saying. And then that's sort of it. So I introduced these 3 methods that we have for smooth trend filtering, change point estimation. And as I mentioned, we are working on putting all of these packages that I was highlighting together in one place. And lots of future work can be done here. I get some motivated students. So, all right, thank you for your time. Yes.
Is there any questions for Dr. Schafer?
Yeah, happy to answer.
I have a question. So I'm not very familiar with the Bayesian version of the change point detection,
Mhm.
but in frequency setup, usually the change point detection is a 2-step process. The first step is we detect a change point, let's say some tau hat, and then we do a hypothesis testing procedure to actually check if that's the change point. So here, in this particular work, we have detected a number of change points. But is there any counterpart which actually matches with the hypothesis testing part in the frequency setup, which actually tells us, okay, the change point is detected, this is the number, but this is actually close to the true change point, apart from the empirical evidence?
Yeah, it's very hard because there are no labeled real change points that exist. Change points are just something we mathematically define. Yeah, so we are not doing any hypothesis testing. We're just summarizing our posteriors everywhere. And then we, as the model, the people who are fitting the model, have to decide if we think that this is supported. So for example, I mean, we do have everything in simulation where we do have true change points, but what was I gonna say? So like here, these locations are only because we summarize our posterior to portion of times when those thresholds, this portion of time when the threshold was 1. And we use that information to say where the change points are. So I can show for some of the count extensions that it doesn't quite work very well. So this is an example of count data. So that same thresholding mechanism with negative binomial likelihood. And you can see with your eyes, like there are some regime shifts, but the evidence that we get from the sampling is not very strong. Like we don't ever pass 50%. So right now it's very much ad hoc, like on the user to decide if it's like strong enough. But, yeah.
Another question?
So how does this compare like computationally to just doing like a full Bayesian lasso, reversible jump expensive thing?
Oh, it's really fast. Like this is like in minutes. from 500,000 samples for a negative binomial. Everything is in RCPP except the negative binomial parts. I coded it myself. And the student coded.
You get negative binomial in RCPP.
Yeah, I know, but I'm saying I didn't. I piecemealed it with someone else's code. So like if you do the Gaussian case, it's probably under a minute for the dynamic shrinkage prior. It's a lot faster than the negative binomial one, especially I highly do not, you can look in the technometrics papers, they're, I think in 2 out of 3 of the papers, there's computational time reported. Yeah, as you're talking about this, because in the Poisson case, you actually, I actually would not recommend using, so if you actually have Poisson data, I actually do not recommend using our method. I would probably use this because the Fourier gamma, as your counts get larger, it gets much slower. So we have the equivalent plot of this in the supplement for the time. And the negative binomial one goes like way much slower. But yeah, I don't know, I guess reversible jumps probably more like hours.
And for fused lasso, it's not necessarily that bad, but the hyperparameter tuning can get really, really hard,
Okay. Yeah,
especially for the breadth depth, like hyperparameters.
yeah, I would just use,
It's fun.
I would just use this 2-stage thing. If you want to inspect something really fast. Honestly, the thresholding model is very finicky.
I think that's the main reason that I've seen people do the Bayesian reversible jump thing, because then you actually do get like uncertainty on where the change point is.
Yeah, so this one you don't get anything here. Yeah, on the uncertainty, like, so. Optimization will only give one place for each. Yeah, so that is a trade-off with this one. Yeah.
Any more questions for?
You guys have any other questions in general?